Hello and welcome to Slice of Physics. I'm going to be talking about electric potential as it relates to point charges and capacitors. So before I talk about electric potential, I'm going to be talking about regular old hill contour maps like we've talked about sometimes in the past. So if I have a hill that looks like this, so it's steeply sloped on the left and less steeply sloped on the right, then its contour map might look something like this. So you see how on the left there is a steeper slope, and we show the slope arrows pointing a long slope arrow here and a short slope arrow over here to show that it's less steeply sloped. And the slope arrows would point perpendicular to the contour lines, and they would be short on this side, and they would be longer on this side where the slope is steeper. Okay. So if I were to describe this hill in terms of height, I would write 10 meters here, maybe, and I don't know, 5 meters here and 0 meters there. Okay. So what if I have a ball that's rolling down this hill, and it rolls from the top and it rolls down to the bottom, and let's say I know the mass of this ball is equal to 1 kilogram. Then, and I also know that g equals 9.81 meters per second squared, which is about 10. G is about 10 meters per second squared. So using this information, I can compute the energy of the ball, which is equal to the potential energy of the ball is mgh, where h is the height of that point at the hill where the ball is currently located. So if the ball is here, then maybe it would be at this 5 meter mark, and then its potential energy would be 1 kilogram times 9.81 meters per second squared times the height 5, which would be about 50 joules. So I can draw a potential energy map. I'm going to draw the potential energy map up here, and since the height and the potential energy are basically the same except one is multiplied by mg, then the potential energy map is going to look the same as the height map. The only difference is going to be this is not going to be 0 meters, it's going to be 0 joules. And this is not going to be 5 meters, it's going to be 50 joules. And this is going to be 100 joules. So this map just shows the potential energy that the ball has at each of these points on the hill. So now we're going to do the same thing for charges. So let's say I have a charge here, and I'm going to bring in a little charge. So this is going to be called Q1, and I'm going to bring in a charge Q2, and I'm going to put them next to each other. Now I know that it requires some amount of energy to do this. It requires some force, because I know that the plus charges don't like to be pushed together. So when I bring in this plus charge, it's going to take some force and some work in order to bring it here, and I'm going to have to use my arm muscles to do it, and I'm going to have to burn some energy. I'm going to have eaten some cereal for breakfast, and I'm going to burn up some of that energy I got in order to bring this plus charge close to the other charge. So the question is, how much energy do I have to use to bring these charges together? One way of thinking about this is that there is an energy hill here. So there's a contour like this, And what this contour says is that all of these points have the same energy. So if I were to bring the plus charge to this point, and then I were to move it around the circle, that would require no extra energy. All of these points require the same amount of energy to get there. If I were to bring it even closer, that would require more energy. If I don't bring it as close, then that would not require as much energy. Out here it would require even less energy. So just like with the ball and the hill, we can label these contours as having particular energies. So to get the plus charge to this point requires 10 joules of energy. To get it to here requires 20 joules, 30 joules, 40 joules, and so on. And you can see how these contours get closer and closer together, meaning that the hill is more and more steeply sloped. So if I were to draw the slope arrows, they would point outward, and the long slope arrows would be towards the center, and the short slope arrows would be out here. Okay. Now this charge has a particular charge in coulombs. Let's say that this is 2 coulombs. Let's say Q2 is 2 coulombs. That's a lot of charge, but I'll just use it so that it's easier to make the calculation. Okay. So before I had an energy hill and a height hill. So I have an energy hill. What will take the place of the height hill? So instead of the height hill, I will have the electric potential hill. So before we had mgh was the energy. This was the energy, and this was the height. Now what we'll have is, and that was the energy. U is for energy. So now we have U equals QV. This is the energy, and this is the potential. So the potential hill is kind of like the height hill. It's going to look exactly the same as the energy hill, just like the height hill looked exactly the same as the energy hill. So in the potential hill, there's these contours, just like before. And to find the potential, we should do U divided by Q. U divided by Q equals V. So instead of 20 joules, it looks like this is the 20 joule line. Instead of 20 joules, we should divide by 2 coulombs, and we get 10 volts. And then here we have 30 joules divided by 2 is 15 volts. And if I were to draw this outward one, it would be 10 joules divided by 2 is 5 volts. And this would be 20 volts. So this is the number of volts in the hill, which is kind of like the height of the hill. So if you think about it, the height of the hill does not depend on the mass of the ball. The hill has the same height. I could roll up a bowling ball up the hill, and I could roll a tennis ball up the hill, and the hill would have the same height for both balls. But the energy of the ball would be different. So the bowling ball, to get it to the top of the hill, requires a lot more energy to get up there than the tennis ball does, because it has a bigger mass. So likewise, if I push a big charge up to the top of this potential hill, it will require a lot of energy to get it there. So the energy depends on the charge, just like for the balls, the energy depends on the mass. But the potential of the hill is like the height of the hill. It's the same no matter what you're rolling up the hill. So if I look at these hills from the side, here's a plus charge, and I look at its hill, it looks like this. It kind of looks like a volcano. It's this really steep when it gets to the top, and then it's really shallow when it gets to the sides. And its formula is energy equals K times Q1, and Q1 is this charge here at the center, and Q2 is the test charge that we bring in like the ball. So this is the This Q1 is the charge at the center that's making the hill. And this Q2 is like the ball that we're rolling up the hill. And that's divided by R. And if I draw the potential version of the hill, which was like the height of the hill in the gravity example, the potential is just K Q1 over R. So it's missing the Q2 because the potential doesn't care what you're rolling up the hill. It's going to be the same potential. Just like the height doesn't care what you're rolling up the hill. It's going to be the same height. We can try putting some numbers in here. So for instance, I'm going to do the proportional representation, proportional reasoning trick. So I just want to see what will happen if I try some different numbers. So let's say over here is R equals 1. And I'm just going to do K times Q over R equals 1. And out here R equals 2. And then it's going to be 1/2. 1 times 1 over 2. And out here it's going to be R equals 3. So that will be 1 over 3. So it seems like it gets smaller and smaller. 1, 1/2, 1/3. Now in here, let's say R equals 1/2. Well, 1 over 1/2 is 2. So here the potential will be 2. So the potential is 2, 1, 1/2, 1/3. And if you try some numbers, it turns out that the potential gets really big really quick as you get closer and closer to the plus charge. The potential gets huge. So that hill just goes steeper and steeper and steeper. Okay. So let's try another one. If I have a capacitor and it has an electric field, remember that the contours, the potential contours between these capacitor plates are like this, right? They're evenly spaced because the electric field is uniform, is constant everywhere inside this capacitor. And in this case, if I look at this hill from the side, it looks like this. That's the hill, right? It just slopes down to the right. And if I were to measure a certain distance here, delta x, the height of this hill would just be proportional to delta x. So the difference, if I take 2 points on the hill like this, and I want to find the difference in height, delta v, remember the height is like delta v here, is like v here. The change in height between these 2 points is just going to equal the slope of the hill times delta x. And the slope turns out to be the electric field. Remember, because those arrows are slope arrows. The slope arrows are also electric field arrows. The electric field is the slope of the potential hill. So that tells me that the difference in potential between 2 points in the capacitor is equal to the electric field times the displacement between these 2 points. Now, of course, that's only true if the 2 points are across from each other like this. If the points are across from each other like this, then they're at the same height on the hill, because the hill slopes down to the right. It doesn't slope up or down. It doesn't slope towards the top of the page or towards the bottom of the page. So now we know a bunch of equations. We know the height of the hill is v equals k q1 over r. And we know that if we roll a ball up the hill, then its energy is k q1 q2 over r. So q2 is the charge of the thing that we push up the hill. And it's like the mass of the ball that we roll up the hill, but in this case the hill is just the electric field produced by a charge, but it's the same idea. And we know that the electric field, which is the slope of the hill, is k q1 over r squared. And finally the force, which is the which is how much the electric field pushes on a test charge, is K Q1 Q2 over R squared. Okay. So here's the complete analogy for the ball on the hill. The ball on the hill has a height, and that height is like the electric potential for the charges. The ball on the hill has a gravitational potential energy, and that's analogous to the electric potential energy for the charges. The hill has a slope, and that is analogous to the electric field. And the gravity exerts a force on a ball that makes it roll down the hill, and that is analogous to the electric force that makes the plus charge run away from the other plus charge. Okay?